All right. Let's see. Is the TV going to turn on? There we go. All right, TV's on. Okay. So first off, welcome back to the wonderful world of mechanics of deformative bodies. I hope you all had a wonderful break, and I know that you all are excited, after you've had this nice break, to come back and have to be with me for 2 more weeks. It's like, I can see you're having a hard time containing your excitement over the whole thing. It was a joke, but not a very funny one, I guess. It's too early, right? Okay, couple things. Let's take care of some housekeeping items first. So, number 1, I have got your homework 6 graded. So I will pass that out. Let me pass the assignments out, then I'll get the solution out. All right, so I think all in all, you all did very well. I can go over the solution if you'd like. I'll probably do it very quickly. It's really not, all in all, I don't think there's a whole lot to say about it, just because I think everybody did very well on it. Oh, I was wondering. There you go. Mr. Harris. There you go. There we go. There you go. All right, let me go ahead and pull the solution up for homework 6. Let me walk on over to the podium. All right, so problem 1, you had to derive the deflection for a beam that's simply supported and has an end moment applied to it. It's kind of funny, we talked about stuff like this in moment distribution and structural analysis, so should be somewhat familiar, right? Apply an end moment and what have you. Okay, so your moment function is pretty straightforward because ultimately it's linear, okay? So once you get your moment function, which is m naught times 1 minus x over L, it's just double integration and boundary conditions as usual, and then solve for the location of maximum deflection. Pretty straightforward. As for problem 2, it really is just doing a little bit of alphabet soup and superimposing your results. That's basically it. I'm going to give you all the solution and let you all sort of sift through that. But all in all, I think you all did very well on this homework, and I don't think there's much to be said. So 1, 2, 3. But does anybody have any questions about it? I know it's early, and you're like, okay, what is this class? What are we talking about? Coffee. Must have coffee. Don't worry, I'm a little bit like that myself. Coffee's a good thing. Okay. Now, next item on the list is homework number 7. I must offer an apology to those of you that have already started it or completed it, and here's why. So I've had some questions on the last problem, okay, and I do want to show you the solution for the last problem, but ultimately I'm going to take the last problem off the assignment, okay? And the reason why is because it's not conceptually a difficult problem. It's actually pretty straightforward conceptually. The problem is that the actual algebra in the alphabet soup gets a little messy, okay? So here's the long and short of it. You have a pressure vessel that's being subjected not only to an internal pressure, but a torque and an axial load. So let me zoom in right here. So if you look right here, first off, the torque produces a TR over J shear stress, which is TR over, the book calls it I sub P. I'll be perfectly honest, I'm really not 100% why they've got the negative sign in there, because it really doesn't matter, and they're not using it here, but that's just me. I think that's a typo. It doesn't really matter whether it's positive or negative, because the radius of the Mohr circle. It's either way, it doesn't matter. All right. Sigma x is going to be generated from two stress components, P over A, which is the axial load, and then sigma sub 2 for pressure vessels. Sigma y is sigma sub 1. So you have a sigma x, a sigma y, and a tau xy. You can then determine principal stresses, using your Mohr circle formula. The problem is the algebra gets a little nuts. Start plugging and chugging and doing the alphabet soup. When you solve for P, the required load in order to produce a given allowable stress, that's the formula. So I apologize if you did that. But it's not that the concept is challenging. That's not really the issue with this problem. It's just the alphabet soup. So I've decided to remove that from homework 7. I apologize if you started that. I'm really sorry. Honestly, I was hoping that not many people had done it. I know that college students that have Thanksgiving break, when they have a homework assignment due on Thursday, it's Wednesday at about 6 o'clock that it's time to start cracking the books. I know things. So so I was hoping that not as many people had started. So I do apologize for anybody that put some time into it. But when I give you the entire solution, I'm going to throw that problem in there just so that you have it, if you want it for future reference and things like that. Okay, everybody good? All right. Let's see, what else? Here's this. Okay, did I get a sign-in sheet started? Okay. No, I didn't because I'm looking right at it. Okay. Last piece of business. As you all are aware, or should be aware, and if you're not, shame on you. Course evals have popped up. So what I do for course evals is this. My structural analysis folks have already heard this because you all are going to get the same deal that they get. I don't know about other faculty, but I really do pay attention to the comments and the critiques I get. I'll tell you a quick story. When I first got here and I taught steel design, I was using these PowerPoints that had a very a dark background. So when you printed it out, the text was white, but the background was when it came out from the copier, was essentially black. And one of the comments that kept popping up is, change the background on your slides because that way we can write notes on it. I was like, that's a good idea. Now my backgrounds look like all my other slides with the Marshall logo on top and whatnot. So you can easily write on the slides. So I take the comments very seriously. If you want to rate me over the coals, go right ahead. I want you to do it, okay? If you think I'm the worst professor you've ever had, that's fine, but tell me, okay? So this is what I'm going to do, all right? So if you look on MU Online, there is a column called the course eval column. If you complete your course eval, bless you, if you complete your course eval and just show me that you completed it, I don't want to see what you wrote, just show me that you completed it. I've had students that have just took a screen capture of their completed survey list, and if Engineering 216 shows up in the list, 10 points. So the way that'll work is this. I don't know how many problems we've had throughout this semester on homeworks, what, 20 problems, 25 problems, something like that. So what I'm going to do is however many points you have accrued on your homework assignment since the semester started, I'm going to add 10 points to your total collected homework average. So if, for instance, throughout this entire semester you've only missed like 6 points total on all your homework assignments, can you get above 100% on your homework average? Yes, you can, okay? So I'm just going to add 10 points on top of that. So if there was a total of, what, 240 homework points, this is going to be 10 on top of that. So if you had hundreds on all your assignments, you could get 250 out of 240. Does that make sense? So that column is currently on Blackboard right now, okay? So you'll see it. I'm going to bring this up on Thursday as well. And just a heads up, unless I'm mistaken, there are folks that have already done the survey in here. And I know in structural analysis, I've only gotten messages from like 6 or 7 folks, but I've had like 12 people do the survey. I'm like, all you have to do is screen capture. This is free points, you know. So now if I get 100%, you know, if I get 20 responses because there's 20 people in the class, I'll just give everybody their 10 points. So everybody okay with that? See, I'm not so bad. All right. Did everybody get homework 6 and get the solution to homework 6? Everybody get that? Okay, the short little solution. All right. Does everybody have a copy of homework 7? Again, I'll send a mass email out, but the last problem on homework 7 is canceled. No problem 4. But I'll go ahead and include that in the solution. But I'll post something on Blackboard and whatnot and have everything there. Everybody good? All right, then let's get into it. So it's a good thing, essentially, that we stopped where we stopped before break. Because this is our last, I guess, really codified topic I want to talk about this semester, which is the elastic buckling of columns. And the thing about buckling is it's a little different from everything else that we've done. It's sort of its own unique animal. So I think it's really good that the way the semester worked out is we covered the broad strokes of the class before Thanksgiving break, and now we can cover this ancillary topic on the side. And if we have a little bit of time, I might talk about like some 3D more circle stuff in here and there, but nothing extravagant, nothing crazy. But this is a really nifty topic, and it's a very important one as well, but it is a little different. So first off, I want to make sure that everybody understands what I'm talking about when I say buckling, okay? And I think the easiest way to understand this is imagine if you had, you know, like a yardstick, and I think everybody in here has seen a yardstick before. If I take a yardstick and I apply tension, I can probably yank on it all day long. But as soon as I take that yardstick and compress it, what happens? It bows out, right? It bows out very suddenly and very weakly. In other words, if you're looking at, here's some numbers for you. A common yardstick can carry over 500 pounds in tension, but if you start applying compression, once you hit about 6 pounds, it's gone, okay? So this is something we really haven't discussed yet, the idea that tensile stresses and compressive stresses can cause widely different responses in a structure. Particularly, compressive stresses have the tendency to cause a structure to lose its stability, okay? And when an element or a system loses its stability under compressive loads, it experiences a phenomenon called buckling. And buckling is associated with large, uncontrolled displacements, okay? The idea with the yardstick, as soon as you reach that magical load, the yardstick gets a little wobbly and whew, it buckles out very large and very suddenly and very rapidly, okay? That's the idea behind buckling, okay? Now, one other point I'll point out about this yardstick, the yardstick itself can carry 500 pounds in tension, but only 6 pounds of compression. But the yardstick, if it's made out of wood, keep in mind the wood itself, the actual material, the fibers of the wood can resist just about as much stress and compression than it can in tension. It's not a matter of the material, it's a matter of the geometry. You have a very large, or a long, slender element, and I use that term very carefully, this term slender, okay, because slenderness has a very specific mathematical definition for us. But looking at this particular yardstick, it's not a function of the material, it's a function of the geometry. A very slender element being subjected to compressive loads, okay? Now, stability can show up all over the place, okay? And it's a very real phenomenon that we need to assess as engineers. If you have a thin-walled cylinder subjected to external pressure, that can cause buckling. Take a Coke can. Large, uncontrolled displacements. If you have a beam that is just subjected to regular old bending, particularly I shapes. If you take steel design, we talk about buckling of beams because think, if you bend a beam, the top of the beam may be seeing compression. Things in compression like to buckle. Steel beams undergo a specific type of buckling called lateral torsional buckling. The idea is you have the beam, you load it, and because the bottom is in tension, the top part wants to buckle, but the bottom part wants to stay where it's at. So the beam ends up sort of kicking out and twisting. So we call it lateral torsional buckling. We're creative in our naming. You gotta love that, right? Another thing that's kind of interesting is if you're looking at a beam, let's say like a really large plate girder on a bridge, sometimes it doesn't buckle due to bending, it buckles due to shear. If you look at old bridges that are made of steel and they got rivets all over the place, you'll notice you've got the beam, but you've got these vertical stiffeners all over the place, these plates that are sort of going like that along the beam. Those plates are there to stiffen the web of the beam against buckling and shear. So, you know, this is a phenomenon that shows up all over the place, and it's very important to assess. Now, to discuss buckling, what I want to do is I want to frame my discussion right now around this problem. Okay, so I have a column, and a column, beam, element, whatever you want to call it. I've got a column that's subjected to a compressive load P. Okay, now the column is L long, EI is constant, and I want to determine what load is going to cause that column to buckle. Okay, sound good? All right. Now I would argue that once it buckles, it's going to look something about like that, right? It's going to bow out laterally, something like this. Now, one thing to note, if I apply P on the top, bless you, if I apply P on the top, statics tells me I've got P on the bottom. Sound good? Okay. All right. Remember, my secret weapon is a samurai sword or a lightsaber. If I'm a sci-fi fan, I'm going to cut a section at some distance x. Okay? If I cut a section, you know, I do have unknown shears, unknown axial force, unknown moment. Right now, I'm really just concerned about the moment. Now, keep in mind, if this is P is going up, I got to have P going down. But ultimately, what I care about is M. How much moment is in the element, or in the column, in the beam, whatever you want to call it. So if I sum moments here, what do I have going on? Well, I don't have anything rotating like this, but what do I have rotating clockwise? Well, I've got my unknown moment that I'm solving for, and I've got P times Y. Make sense? So that means that moment in the section has to equal the load, or negative, the load times however much the column is bowed out. Make sense? Okay, so that's a little, you know, something to think about. You know, the moment in the section is a function of how much it's deflected. That's a little bit strange, but it happens this way when we're talking about stability. Now, I've got moment equals negative P times Y. Now, earlier in this semester, we derived the following relationship. The idea that the second derivative of that deflection is m over EI, right? A very fundamental equation that we talked about, what was it, like week 9, week 10, something like that? Okay, so y double prime, you know, instead of, because I'm lazy, I don't want to write the derivative over and over again, I'll just say y double prime is m over EI. Everybody okay with that? Okay, now the moment itself from our section cut is negative P times Y, so moment equals negative P times Y. That's how I get this. Sound good? All right. So, rearrange this, pull everything over to one side, and I get Y double prime plus some constant times Y equals 0. Now, to make the math simpler, okay, I'm going to make something up. I'm going to take this term, and I'm going to call it alpha squared. Okay, I'm doing that to make the math a little simpler. I can call it whatever I want. I'm just sort of renaming it. And I'm calling it alpha squared just because of the way the math will work out. Everybody okay? So that means I've got y double prime plus alpha squared times y equals 0. So I have got a second order, oh man, I mean, the C word, calculus, that's one thing, but not the D word, not differential equations, not that, right? So there's a number of ways to solve this. I know how college students will solve it. I know things. Like I don't know things. Come on. I've been around. So y double prime, what's that? Oh, okay. Plus a, and then alpha squared times y. You can see it's a common differential equation. Okay, so I just use a because I'm not going to type out the alpha. Uh-oh, it's computing it out. And there's our differential equation solution right there, right? C1 times the cosine plus C2 times the sine. Now, if I want, I could write a characteristic equation. I could turn the second derivative into r squared. I could turn the original term into just 1, solve the characteristic, get imaginary roots, and then imaginary roots are complex conjugate pairs. I know my friend here who loves differential equations, he knows all about that. But all in all, solving that differential equation yields C1 times the cosine plus C2 times the sine. And it's sine of alpha times x. The reason why I called this alpha squared is because I knew the solution was going to yield alpha. I didn't really want to deal with square root of p over EI. I didn't really want to deal with that. So, you like that reference? That whole Wolfram alpha thing? I know things. So, okay. Now, much like beam deflections, we have two arbitrary constants that we need to assess, right? We've got C1 and C2. So this is no different than any differential equation. In order to solve for those unknown arbitrary constants, we need boundary conditions, right? I propose that even though we're dealing with a buckled column, the deflection here and the deflection here, this is x equals 0 and this here at the top is x equals L, I propose that those deflections are 0. Sound good? Okay. Now, so let's utilize our boundary condition. Let's do the first one. The first one says that the deflection at 0 equals 0. Sound good? So here's our expression. Plug in x equals 0, x equals 0, x equals 0, and this whole thing must equal 0. So C1 times the cosine of 0, C2 times the sine of 0. What is the sine of 0? Cancels. What is the cosine of 0? 1. There we go. C1 equals 0. Nice. Simple, right? Now, next one. So this whole term goes away, and I'm just dealing with y equals C2 times the sine. Now, I propose that at x equals L, so L and L, this has to be equal to 0. Sound good? Now, there's a problem with this, okay? We need to find where that equals 0, okay? Where C2 times the sine of alpha L equals 0. But we need to think about this, okay? Let's go back to basic math. Remember that whole zero product rule? Remember that? That if x times y equals 0, either x is 0 or y is 0. Remember that? Okay, all right. So let's look at this. There's a couple ways that this could be 0. Just looking at this expression. Would you agree with me that if this is 0, C2 is 0, that this is valid? Just this equation. Ignore the points down here, but if that is 0, this expression is valid, right? Okay, that's fine. Here's the problem with that. Here's my expression for deflection. If that is 0 and that is 0, it's telling me the column hasn't deflected at all, and I know that's not true, right? If I load that yardstick, it's going to bow out, right? So C2 is what equals 0 is what we would call a trivial solution. It doesn't yield anything that makes sense, okay? Now, let's look at this. What happens if L equals 0? I get the sine of 0, which is, so that works, right? But that doesn't make any sense either, because if L equals 0, I'm saying the column has no length. It doesn't make any sense either, right? The column's got to have some length to it in order for us to be talking about a column, right? I could say alpha equals 0. That would work, but that's trivial too, because remember what alpha equals. Alpha is this, P over EI, or alpha squared is P over EI. If alpha equals 0, I'm saying the column has no load on it. Well, it doesn't make any sense either. But now I'll go back to that zero product rule. Zero product rule states that if x times y equals 0, either x is 0 or y is 0. What about this entire trig function? Maybe that's not so trivial. When does the sign equal 0? 0, pi, 2 pi, 3 pi, 4 pi, even multiple integer, even integer, or not even, just integer multiples of pi, right? Right? So I propose then that a non-trivial solution, a solution that's actually going to give us something that makes sense, is when this internal quantity is n times pi, where n is 1, 2, 3, 4, what have you. I'm not making it 0 because then that says either that 0, and goes back to being trivial. So this alpha term is n pi over L, and n just is, 1, 2, 3, what have you. Sound good? Okay. So alpha squared is P over EI, but alpha also equals n pi over L. Just set the two equal to one another, solve for P, and there we go. That is the load that causes buckling. But there's this pesky little n term in there, and yeah, we know n is an integer, but what does it really mean? I mean, what does it mean if n equals 2? What does it mean if n equals 3? Okay? These terms n are related to what are called buckling modes, or related to the buckled shape of the structure. In other words, we have an expression for the deflection and for the load. Okay? And this term alpha can just be n pi over L. What ends up happening if you use different values of n is you get different means by which the structure deflects. Now keep in mind, we're assuming the structure deflects in a sinusoidal-like fashion, where we get that sine curve. But that makes sense when you think about it. For instance, if n equals 1, we've got a sine curve that looks something about like this. That term n serves to change ultimately the frequency of that curve, so n equals 2 looks like this. N equals 3 looks like this. And if I kept increasing n, I would get a different buckled shape. We call each of these buckled shapes a buckling mode. Okay? Make sense? Now let's just go back to common sense. All right? If I take a yardstick and go like this, what's it going to look like? 1, 2, or 3? 1, right? Make sense? Not only that, but look at the loads. The load required to induce this buckled shape is n equals 1, right? Here's the buckling load, P squared EI over L squared. To get it to look like this, I need 4 pi squared EI over L squared. To get it to look like this, I need 9 pi squared EI over L squared, right? Now if I start taking that yardstick and going like this, which load am I going to reach first? That one, or that one? One on the left, right? Makes sense. I propose to you that load on the left is the critical buckling load for a column, okay? That is one of the most fundamental stability formulas that there is. If I take a column, yardstick, what have you, I apply a load, that is when that column will experience buckling, okay? Make sense? Does anybody have any question about that? I want to make sure that's clear. Everybody good? What's that? That's a very good question. Okay, and the easiest way to answer that, because I'm a civil engineer and I refer to everything in civil engineering terms, is let's say I've got, a building, and I've got, some column in the building, and then let's say I've got a beam framing into it here.
Oh, so it has to be 0 at 2 different points.
What's that?
The deflection has to be 0 at 2 different points.
Yeah. this point right here would be what would happen if you braced that column, or if I had a brace here and here. And that opens up a whole can of worms. I mean, stability could be a class in and of itself. We could talk all about stability of beams, stability of plates, stability of columns, and bracing and different modes of buckling. We could have a whole class just on that. So, but the simplest answer is if there is a brace there. Does that make sense? Because essentially what you're doing when you have a brace there, you're cutting the length in half. So if you've got L over 2 squared, that's that L squared over 4. Flipped up, that's why the load multiplies by 4. Does that make sense? So that's a good question. All right. Did I answer your question? And everybody else? Yes, sir. Are you talking about like that classical bridge back in the fort? Okay, that is not really. I'll give you a simple answer for that, and it is an oversimplification because what happened with the Tacoma Narrows Bridge is related to structural dynamics. Okay. The easiest way I can answer that is this, and there are going to be a little bit of inaccuracies in my answer. How many of you have ever played a guitar? Played a guitar. Okay. All right. One of the things you'll find with a guitar is, let's say you play the top string, you play that string and you play it either very softly or you wail on it. Okay. It might sound a little rougher, but all in all, it produces the same note. Right? Make sense? Okay. The reason why is because there is a fundamental property of structures, and that is under free vibration, they all vibrate at the same frequency, their natural frequency, if you will. That's why if you take a guitar string and pluck it very lightly, or pluck it very hard, or somewhere in between, it might be louder, it might be at a different amplitude, but the frequency is the same. Make sense? Okay. All right, so each structure has its own natural frequency. It's not just guitar strings. Buildings have their own natural frequency, and bridges have their own natural frequency, and what have you. It's a very important quantity for us as structural engineers when we look at earthquakes. And it's a very important concept for you mechanical engineers because machines go blah, 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 they, you know, I mean, blah, 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 right? Machines vibrate, you know, so vibration and structural dynamics go hand in hand. And there are actually a lot of mathematical similarities between vibration analysis and stability analysis. There's a lot of mathematical similarities there, okay? All right, but going back to your question. Okay, now, how many of you have ever seen that old classic film or image of the opera singer in the wine glass, and they sing and they crack the wine glass? Okay, the reason why that happens, okay, is because the wine glass, like the guitar string, like the building, like the bridge, has its own natural frequency. You know, you clink the wine glass, it goes, right? Well, what the opera singer is doing is they are producing an auditory vibration with their vocal cords that matches the frequency of the glass. And it creates a phenomenon called resonance. And when you apply a load to a system at its natural frequency, it just builds on itself and it fails. In a roundabout way, that's kind of what happened there. But even that answer has some inaccuracies to it because there's a lot more going into it. That's a simple answer. But you have stumbled on something that's kind of interesting because vibrations and stability from a mathematical perspective do have a lot of similarities. For instance, how many of you have had linear algebra or had a course in linear algebra? Has anybody heard of an eigenvalue? Okay, so a few of you have heard of an eigenvalue. Okay, when you start doing complex stability analysis and you search for buckling modes and buckling loads, they are very closely related to a structure's eigenvalues. Okay, the same thing is true for their natural frequencies. In other words, when you do a vibration analysis, it's funny how its natural frequency is derived from its eigenvalues. So there's a lot of mathematical similarities between the two. So I love this stuff. I can talk about this stuff all day. And just one more just to get it out. Right? Is that like that? Technical terms, right? talking about resonance and natural frequencies, but at the same time throwing in sound effects. This is good stuff. I like it. All right. Did I answer your question a little bit? And everybody else? This is good stuff. Okay. So I propose that the critical buckling load, pi squared EI over L squared. All right. Now, I'm going to rewrite this another way. I want to compute an equivalent buckling stress. Okay? Equivalent buckling stress, well, how do I calculate stress? P over A, right? Sound good? All right. So pi squared EI over L squared, I'm going to pull the I out. Now, if I'm dividing this by A, I get this term in parentheses, I over A. Okay? I over A is a section property, just like area, just like the centroid, just like J, just like moments of inertia, what have you. It is a section property, I over A. And it has a very special name. We call it the radius of gyration. Okay? I mentioned this a while back. Remember, when we were looking at section properties, we said, okay, here's the moment of inertia, here's the section modulus, and then there's this term R. I said, we'll get back to R. Okay? R is the radius of gyration. And if you want to calculate it just to see how it works, like if I'm taking axis 1, 1, and I'm looking at the 30 by 211. So here's the moment of inertia, here's the area. Take I over A and take the square root, that'll give you 12.9. That's the radius of gyration. They're just making your life a little easier for you by recording it. Sound good? Make sense? All right, so the radius of gyration has a pretty important relationship for us in the world of stability when we look at slenderness. Okay, so watch this. So critical buckling stress, pi squared E over L squared times I over A. Okay, well, I over A, that's R squared. So if I do a little bit of algebra, I can rearrange this term. Instead of saying pi squared EI over AL squared, I can say this. Pi squared E divided by this quantity, L over R. L over R is what we call the slenderness of a given element. In other words, the length of an element divided by its radius of gyration. Slenderness gives us a mathematical description for a given shape as to how slender it is. In other words, the L over R for, let's say, that coffee cup is going to be much higher than the L over R for this pencil. Okay? This pencil is much more slender than that coffee cup, right? The reason why is because this pencil has a much higher L over R than that. It is a much more slender element, so it has a higher slenderness value, higher L over R. Does that make sense? Okay. Now, the units of R are length. You know, a radius of gyration is like 12.2 inches, 3.6 inches. So another nice thing about L over R is, what are the units of L over R? Unitless. The nice thing about slenderness is it is a unitless expression of a measurement slenderness. So that's one of the nice things about it. All right. So far, so good. The last thing to consider right now for our perspectives is the boundary conditions. When we did our derivation and went through all of this, we assumed that. We assumed a column that was pinned on the top and pinned on the bottom, or simply supported. And whether or not this is a pin or a roller, for the purposes of our discussion, is not really going to matter very much. But, let me skip ahead a little bit. What if the boundary conditions were changed? What if the column was fixed on the bottom? What if there was no boundary conditions on the top? What if it was free to buckle? How does that change the answer? Well, first off, does it change the answer? Yeah, it does. Okay? All right. Changing the boundary conditions ultimately changes the way the structure is going to buckle. I want to consider this column. This column is a fixed free column. Okay? Now, I would argue that if I take this column and apply that load, it's going to buckle something about like that. Right? That's a pretty reasonable assumption. Okay. All right. I want to relate this to what a simply supported column looks like. Okay? And I'm going to show you how I'm going to do that. All right? Here's the simply supported column, right? Now I'm going to introduce to you a new term. This term is what's going to be called the effective length factor. It's going to be called K. Okay? Now K helps us relate what an arbitrary column looks like, what the comparison is between some arbitrary column and that column. Why that column? Because that's the column we use for our derivation. So this column is sort of the baseline. For this simply supported column, K would be 1. Let me show you what K would look like for another column. Remember this? The fixed free column? Well, if I took that shape and sort of extended it, see how this total buckled length looks something about like that? You know, it's the same buckled shape. I'm looking at the distance between inflection points on that curve. Going back to you calculus folks, love all those mathematical terms. We're looking at the distance between the inflection points, okay? That change in concavity, right? Okay. I propose that the equivalent or the equivalent effective length of that column is 2 times its length, because I require that much length to be able to compare it to that of my baseline, my simply supported column. So for this fixed free column, I use a K of 2. Make sense? Everybody okay with that? So I can adjust my critical expressions for load and stress. Instead of being pi squared EI over L squared, pi squared EI over KL squared. Or sigma critical as pi squared E over KL over R squared. Sound good? You folks that decide to take steel design, this stuff's going to pop up again, because we spend a lot of time talking about buckling in there. All right. Everybody good? Okay. So here's some summaries for some K values for some pretty basic conditions. So for instance, if you have a pin-pin column like a typical one, K is 1. If you have a fixed free column, K is 2. Okay? Now a couple others, if it's fixed on one end and pinned on the other, we have a K value of about 0.7. Okay? And if it's fixed on the top and fixed on the bottom, K is 0.5. Okay? Make sense? We have our nice little formulas for elastic buckling load, elastic buckling stress, and then the radius of gyration. All right? This would be a slide that's probably worthy of a star, you know, something to put in your notes. Excuse me. Does anybody have any questions? Hold on for one second. Actually, I think I gave you the wrong one. Let's see that. There's that. Actually, the handouts and whatnot, that I gave all that a while back, but I'm going to bring the notebook around on Thursday. So, all right. Any questions? Okay. So I want to go into the following problem to kind of just make sure we're assessing what's going on. Okay. So I have a wooden element. It's 2x4, and we're going to use just the 2 inches by 4 inches. You, civil folks and anybody who's been around lumber knows that 2x4 is not exactly 2 inches by 4 inches, but I don't worry about that. We're just going to use the dimensions just to make our lives a little easier. All right, so 2x4 wooden element is used as a column with fixed ends. What's K? Okay, all right, make sure we're paying attention. All right, so for wood, we're going to take E to be 1600 KSI. Now, I want to determine 2 things. Number 1, what is the column's maximum permissible length if I can't get to 5 KSI? And what central load can be carried if the column, with the column, I have an extra if in there, so ignore my carried. That's the one that needs to go. It's like I needed my coffee when I wrote this. What central load can be carried if the column is 8 feet long? All right, everybody good? Okay, all right. That's going to bug me. I'm going to go ahead and change that now. All right. So let's get into some math. 80 pages. You see that? We've done 80 pages of this stuff. Whew. Example 32. Okay. Now, the first thing that I'm going to do for this problem to make life a little easier is I'm going to compute some section properties. Okay. Now, all right. Now, remember, we're dealing with a 2x4, 2 inches by 4 inches. So, since it's been a while, let's start off with something simple. What's the area? What's that? Yeah, there we go, BH. Okay. Sound good? Now, let's start off, let's increase the difficulty a little bit. What's the moment of inertia? What's I? Well, that's the right formula for the x-axis, but that's not the one we're going to use, and I'll explain. First off, let's go ahead and compute that. Okay? So I'm going to call that Ix. Remember the strong axis? Okay, so let's do that. Ix. So BH cubed over 12. So 2 inches, 4 inches cubed over 12. Bless you. What does that come out to be? Ten point what? 6. We'll just leave it that. Inches to the what? 4. All right. Now what about Iy? How would I compute the moment of inertia about the y-axis? If it's bh cubed over 12 for the x-axis, what's it for the y-axis? There we go. B cubed h over 12. .67, something like that. There we go. 2.67. All right. Now, what do those numbers mean? Let's go back to bending. Moments of inertia are a measure of the stiffness of a given element in different directions. Remember the wooden joists in your deck, your outside porch or something? Remember, why do we face them up this way versus that way? Because they have a higher moment of inertia in this direction, right? Okay, now I want to go back to the yardstick. All right, so we'll try my 3D art skills. Let's see what I can do. So here's the yardstick. All right, so right? Should I sign the artwork or something? Well, thank you. Now, here's me. I've got the yardstick, and I'm loading it. Now, help me out. Which way does that thing want to buckle? Does it buckle, let's see, like this? You know, out like that? Or does it buckle down? I'm trying here. In other words, here, let's do this. Does it buckle downward or does it buckle out? It buckles out, right? In other words, if I got that yardstick, it bows out along that long side, right? Why? why does it buckle along that long side? Say it again. It's weaker. I propose that with that yardstick is much easier to bend that way than it is to bend the other way because of its moments of inertia. It's so much larger in this direction, you can tell it when you feel it, right? Same thing's true here. I propose then, when I calculate my radius of gyration, R, I'm going to use Ry, square root of Iy over A. Make sense? What does that come out to be? He's making us do math. We just got back from break. Say it again. 0.58, something like 0.577, something like that. Okay. Sound good? So that is a measure of, you can kind of think of radius of gyration as kind of like a normalized measure of how much area is removed from the centroid. I think it's about the easiest way to describe what it is. All right. Sound good? Okay. All right. Last thing, I'm going to go ahead and write it out. Effective length factor. K. How much did you say K was? 0.5. And this is because we've got a fixed beam. All right. Sound good? In other words, we're clamping those ends so that not only can they not move, but they can't rotate as well. We're clamping the ends of it. Everybody good? Any questions? All right. Let's go then to each part. Okay. Let's determine the following. First off, part A. What is the column's maximum permissible length if we only allow 5 KSI? Okay? So, let me ask you this. What is the stress in that column going to be? In other words, if I apply a load to that column, what is the stress? What is the buckling stress? How do we calculate buckling stress? There you go. Pi squared E, remember it's square, pi squared. Pi squared E divided by KL over R squared. All right? Sound good? So, sigma critical is pi squared E divided by KL over R squared. Now, in this quantity, we know what E is. That was given to us. And what's E? Not 16,000, 1,600, right? Is it? It's 100, right? Yeah. All right. 1,600 KSI. We know what E is. Now, sigma critical, what we're going to do is we're going to say, all right, we need to know what the length of the column is such that that reaches 5 KSI. So we're going to know this. What I'm going to do is solve for KL over R. Now, how do I solve for KL over R? Well, I propose that we do this. So I'm going to switch the denominator. So KL over R squared is pi squared E over sigma critical. So KL over R is that. Right? Everybody okay with that? Now let me do this. So I'm organizing my thoughts. Let me do something real quick. What's that? You're exactly right. You're exactly right. So first thing I'm going to do is I'm going to move this down. And I'm going to say this is part A. And for part A, we're saying sigma critical equals sigma allowable, which is 5 KSI. Just so I'm differentiating between part A and part B. All right. Sound good? Sorry about that. I should have put a heading up there earlier. Come on. All right, fine. Be that way. All right. Sound good? So what you were saying, we're solving for L. So L is R over K times the square root of pi squared E over sigma critical. So let's plug and chug. So what do we have? R is what? Yep. And what's K? 0.5. Pi squared times E, what's E? There we go. And sigma critical is, all right, yeah. So what does L come out to be? First off, numerically, what's it come out to be? Say it again. Okay. 64.85 what? Inches equals how many feet? Like 5.41, something like that? Yeah. Is that too bad? Pretty straightforward, right? Simple stuff. Any questions? All right. Now, let's keep in mind that part B is a separate problem. Okay, it's completely separate. All right. So when I do part B, it's going to be like I'm dealing with a whole another example altogether. Does everybody have this? Because I'm going to go ahead and move on to the next slide. All right. So what's going on with part B? Let's read that out again. So part B, what is the central load that can be carried if the column is 8 feet long? So in other words, L is 8 feet, and what am I solving for in this one? What? P. All right, P. So just want to make sure that makes sense. Okay. Now, so L is 8 feet. Now, L is 8 feet, but what I'm going to do right now is I'm going to say equals 96 inches. Okay, and you'll see why here in a second. Ultimately, it has to do with E, because E's in KSI. Now, and I is in inches to the fourth. I guess I should add that. Now, if L is 96 inches, what's KL? Yeah. There we go. Now, sound good? Tell me, how do we compute P critical? There we go. Sound good? All right. Oh, goodness. All right, so tell me what to write. So we have pi squared. What's E? Now, help me out. Somebody else. What is I? Well, we could substitute that if you want, but since we have the i's already computed, we might as well use them. The question, though, is which one? There you go, the 2.67. We use the smaller one. And what KL, and we have KL over here, that's 48 inches squared. What does P critical come out to be? Say it again, 18.3? 18.3 what? Kips. Now, that is the answer, but I do want to check something, okay? I do, just for the heck of it, I want to say, all right, let's put our blinders on and forget all about buckling. Ignore all this buckling stuff. If I told you there was 18 kips in compression on this 2x4, how would you compute its stress? Ignore the buckling stuff. P over A, right? Load over area. So let's just compute that. So I'm just going to say, you know, note, sigma axial is P over A, which is 18.3 kips divided by, what's the area? 8 square inches. What is that? .2829, something like that. 2.8. 2.28 what? KSI. All right. Now, that's less than or equal to sigma allowable is 5 KSI. Okay? There's a very important observation to make about this. Okay? What I'm going to say is that therefore elastic buckling occurs. Now, what do I mean by that? Well, yeah, but you are correct by the elastic part that it will return to its original shape. But what I'm saying is that because that value is less than 5 KSI, I'm saying buckling is going to happen altogether. Let me put it like this. So let's go back to our yardstick. You would agree that if I took a yardstick and did that, it's going to buckle. And it's going to buckle probably before the wood splinters, right? So think about that. Think about that in your head. I do this, the wood will buckle, and then it will splinter. Now, let's say instead that it's cold, and you know, when temperature rises, things heat up. So, so I decide that if I have a wood-burning stove, I want a log for the fire. Okay, so I go out and I get a log. How many of you all have chopped wood before or seen chopped wood? Okay, so there we go. It's West Virginia, and what do you expect? All right, so let's visualize what like a fire log looks like. I mean, it's about like that, about yay long. Okay. Now, obviously, it's going to take more load to fail that log than it will the yardstick. So let's imagine that I got like a large capacity press or something, and I put that log in the press. Now, is it going to behave like the yardstick? Is it going to bow out, or is it just going to and splinter? It's just going to smash, right? Now, why is it that the yardstick buckles, but the log just splinters and smashes? Why? Slenderness, exactly. The yardstick is way slender. The log isn't, okay? It's still wood. It's not like the behavior changed because, wood is wood, okay? But it's the geometry. The yardstick is inherently more slender, so it fails under stability. In other words, the yardstick will buckle before it crushes. See, if we had done this calculation and we got sigma axial was like 15 KSI, what that means is, well, yeah, that's what load will cause it to buckle, but it'll crush before it buckles. Does that make sense? So it's all about using, a little bit of common sense. I mean, you could calculate a buckling load for a log, and you would probably get some crazy number, some thousands of kips. But it only takes about 15 kips or 20 kips or what have you to crush the log. Make sense? So it tells you that for the log, stability isn't a problem. It's going to crush before it buckles. But for the yardstick, different story. Does that make sense? That's the point I wanted to make with this, okay? And that's a really subtle point, but it's important, okay? Because those types of points matter in determining behavior and ultimately determining design. If you're going to design some load for compression or some element for compression, you got to know if it's going to buckle or not. Maybe it doesn't buckle at all and just sigma equals P over A. Maybe it does buckle and all, and it becomes a different story altogether. Thanks. What's that? Well, I don't want anything to pop. No, but you're right. If buckling isn't an issue, then we still have the same factors of safety that we need to apply and all that. But you're exactly right. Yeah, I mean, regardless of that, we still have our factors of safety and our allowable intolerances and what makes us feel safe at night. But if it pops, I'm going to Costa Rica or some non-extradition treaty country or something like that. All right, real quick. So I do have one final homework assignment for you. Unfortunately, I forgot to print it, but it is a column assignment. It is 3 problems. It will not be due until next Thursday, so the 8th, okay? So real quick, let's make sure we cover all the bases for everything that we need to discuss today. So you all have been returned homework 6. I will send emails to make sure everybody's on the same page. Homework 7, I am eliminating problem 4. Homework 8, I will bring hard copies on Thursday. Okay? Homework 9, I know there's no homework 9. Funny guy, right? All right. Homework 7, okay, due 2 days from now on Thursday. Homework 8, due 9 days the following Thursday. Course evals, send me confirmation that you have just done it. I don't want to see what you wrote. I just want to see your completed survey list. Automatic 10 points added to your total homework average. So again, if you've only lost 7 points on your homework since the semester started, can you give above 100% on your homework average? Yes, you can. Okay? Just send me. I've had people walk up to me with their phone and just say, does this work? And that's fine. I'll mark it down. Sound good? All right. I will send emails today, making sure everything's documented. That's all I got. See you on Thursday.
Are you the only one who gets to read their course evaluation?
Am I the only one? Not, well, after the semester's over, and even then the answer is no, because we turn them in for tenure and whatnot. So, but you can write whatever you want. Oh, go ahead. Oh, I've got some good stuff. Here.